Sweet. Looks like we're live. Alright. Do some sound checks. Sound check. I think I'm soft. How about sounds better? Really got to work on figuring out the mic thing here, I guess. How's that? Maybe. I think we'll do. If I turn this up a little more, I could also just talk louder, right? Maybe I'm just whispering. My AC is also just makes this obnoxious background sound. So that's what we're hearing. Anyways, welcome. So today we're going to be continuing it off where we were yesterday. As I briefly mentioned, I'm just going through the exercises in the Bayesian Cognitive Modeling practical course book, which is a book on how we can use Bayesian inference in order to understand well, really it's just probability distributions, right? Like we're just trying to extract information from probability distributions, but how can we use this information in order to build models that represent things we actually care about in the real world? And we'll start with some pretty basic examples, and then we move into some more applied examples from the literature, which is why this is really cool, because it demonstrates how this stuff gets used in the real world and breaks it down pretty nicely. So we did the first couple exercises here, and we're just going to continue off, and I believe we're in chapter 3, and we identified the difference between two rates. So we look at posterior prediction. And I briefly read over these chapters, but I'm going to be reading over them as I go along too, so we'll just see what happens. Bayesian analysis provides the bridge from unobserved parameters to observed data. So we want the bridge to be a good bridge, and the best way to check the quality of that bridge is through prediction, or at least that's what is claimed here. And we can talk about 4 different distributions that give us different pieces of information about the quality of our prediction. That is the prior distribution, so what we represent probabilistically via our subjective beliefs about where the parameters ought to be with no information from the data, what that would look like if we just generated some predictions. Then we update our posterior distribution, so now we have an updated set or model of what we care about, and now what would that model predict? And we're just going to start with, it looks like rate test 4. So now I'm just going to move over to the exercises here, and we'll get started. Understanding these ideas is key. Check your understanding by trying other data sets varying with K&N. Okay. So we have posterior prediction and prior prediction. So I'll just open up the data set here. So what this is showing basically, if we were looking at this simple example where we once again have a binomial model and we want to look at the successes of, oh, they don't have the picture, oh there it is. So we observe some total count of trials, and we have successes, and then we have some rate of success, right? And the rate of success and the total number of trials gives us information about how many successes we see, and then we make some assumptions about how these things ought to be distributed, or are distributed, in our opinion. And this is just the JAGS code, or this is the model code, stand code. We have k-bin, it's a binomial, there's data n, and let me just pull up the code now. So I've got my RStudio here open. Let me just make my way over. I realized yesterday that I had it set up so that I was in the wrong working directory, and I only realized that after looking at some of the quality of the footage yesterday, so we'll try to not do that today. So we'll need this, that's our model. Let's get another, I really got to figure out how to change the default so it just always has that extra column, because I like it, because I can do this, I have the model over there, and I can keep a source here. Let's get the JAG code up then. What's the difference between this code? Let's see. I see. This is just using it in WinBugs. So if I was doing bugs. I don't have bugs. Or at least I don't think I have bugs. I'm not sure what would happen. But I know I have JAGs. I'm using a Mac, so there's some complications with getting bugs on the Mac. So I just didn't even venture down that road. I just kind of moved forward with JAGs here. But maybe something to explore in the future. But let's just get to the example then. So I have the model here. Let me set the working directory. Maybe this will work this time now. Let's see if this just runs it. Oh, nice. Yeah. Sweet. So we won't have working directory problems this time. We'll just be able to run through it. So we identify all the samples. Invalid graphics state. Let's just comment out that. Nice. Okay. So here's the example then. I think this is probably the best way to do it, just to explore the cases. So we have the top graph is our likelihood, right? It's our what we modeled as the likelihood, and then the posterior distribution. So in this case, we used uninformative priors, so uniform priors, and then when we observed the data, and we saw, let's see, we only saw one success. So that's information that, we're not that successful out of 15. So it's more likely that the success rate is low, the underlying likelihood. The graph below then is predictions. So if we predicted how many successes we would get, if we tried to predict K using the prior model, we would just get this uniformity, right? We would just see the same distribution of counts across all possible successes for 15 trials, right? So one for each time. I think so. Oh, no, right. So the information from the model tells us that we can have up to 15 possible successes, right? Because we have 15 trials. And the best way to check this would just be, if I change that to 20, or if I change that to 30, you see. So the prior still is saying we have equal probability across all possible outcomes. And as I increase the amount of possible outcomes, it just extends the prior. So we'll go to 15. And in contrast to that, the posterior predictive, or posterior, what is it called? Let's see. I've got the book here, but I like paper copies, so I'm trying to just follow along using the book. So the posterior prediction then, we're examining the adequacy of the model. Okay. This examines the adequacy of what we observed, or what we've modeled. So in this case, the maximum likelihood estimate is somewhere, let's see. I think it's called simple. We need data, right? So let me just get the mean of data. The maximum likelihood for the posterior is like 0.1. So most of our successes then are going to be low, right? So out of 15 times, it's most likely we're going to see a lot more zeros and ones and twos, and then this trails off over based on this particular posterior. Cool. And then we can change this. So say I change this to 10. See, it's moved. I sort of get these. I don't like the legends. It's just, well, better. In this case, now from moving from uniformity, we see because we had a lot of successes, it's more likely that we would predict higher success counts around these across all possible distributions of success counts. So this is a probability mass function for discrete. Probability density function. Or mass function, yeah. Neat. So I think I got that. So let's try different priors on data by changing. So we're going to change the code, and we're going to move from beta to beta 10. So we'll just move through each of them then. All right. So let's change this back to 1. So we have that. We're back to this low success. And now let's just change this. Which so what if we did 10 and 10? But this is interesting because now we've got a count of 10 successes, 10 failures. So that's 20 observations, which is more observations than we actually observed in the data. That might be problematic. I'm not sure if I understand the intuition why that's problematic, but let's see. The neat part about doing it this way, I found, is that I can just, oh, never mind. Oh no, it's good. Yeah. So I can look at the previous plot. So this is what we saw with priors 1, 1. And this is what we see with priors 10, 10. It looks like it might be moving closer to chance. I don't know. Let's do 100 and 100. And see if that gets us to 50 or that takes us all the way to the other side. Oh, yep, looks like it's moving to chance then. Yeah, so this is coming over 50, so now that I have more, so as I increase my sample, I'm getting a more precise estimation of the likelihood. So we're just moving to the 50-50 mark here. So I have strong priors about, right, so this is like increasing the strength of my prior because I have more, I'm saying it's representative of more information because I'm saying it's representative of 100 rather than 1, right? So my prior could be really small then, right? This is one of the example cases. And then it'll be all the way over here because I have weak. This is not uninformative, right? It's informative in the sense that it's telling me these are very, very weak priors, almost non-existent to an extent. Well, no, they are existent, I guess. I wouldn't say that, but small. So that relative to this example here. So this was 1, 1, but the other one was 0, 1. So you see how it shifted to being even more likely or more probable that the true value of the data parameter was very, very low because it means so little information. let's play around with some other examples. So let's do 1 and 5. So this means 1 success, 4 failures, right? Or 5 failures, so 6 total observations. And then I observed 1 success and 15 observations. So my intuition then is that we're going to see a graph pretty steeped up here. Yeah, good. It's like this is like confirming information somewhat. And I wonder if I did 10 and 15. 10 and 50 instead. You can see how the predictions and I think one interesting thing, or one thing that this exercise wants us to see is just the predictions really map on nicely to the probability density functions for each of the prior and the posterior. Let's move to the next exercise. Predicted distributions are not restricted to exactly the same experiment as the observed data. And can be used in the context of any experiment where inferred model parameters make predictions. In the current simple binomial setting, predicted distributions could be found by an experiment that is different because it has n prime or some value of n that's not equal to what we actually observe. Change the graphical model to implement this more general case. So it wants me to change this code and make it so that instead of modeling my priors or modeling my does it want me to change the posterior predictive and prior predictive models to represent something beyond just n? Because n is what we observed in the data, but maybe I it's like having an n2. The predictive distributions can be found by an experiment that is different. So these can be different. And to specify Now I just have to edit the code so that the plot gives me N2 rather than N. See, so the prior and posterior distribution here specified from the data observed, but my predictive checks are on different data. Right. Specified here, my prior predictive is based on N2 and the theta prior. Posterior predictive based on theta and the new data. And I can do is like, I have a case set of 300. Let's see. Do 50. Right, so 50 here. Just demonstrating that what I fit my model and did my inverse, estimated my posterior distribution on, is separate from what I do prediction on here. Alright, so in October, reported out of 120 adults, 24 adults indicated that they had some point been bullied. They said, they called them on that? Nah, that's wrong. So now we're just going to check if they're right and they're theorizing here. Luckily, the code offers some. So we saw 24. So this is just contextualizing the example. So add some meat to it. So out of 121 older adults, 24 here. So we're still using a same prior, but now we have real numbers. We have a real question we want to be able to answer using this technique. And it's about bullying. So 24 folks have been bullied or indicated they were bullied out of 121. He rejected the suggestion that her study may have been too small. If I had more people, the results would have changed by 1 or 2% at most. So they're claiming that with an increased sample, the results would have been different. So this is, I think, where the second n comes in, where like if I had 200 here, so I'm running my probability mass function on more folks. I wonder if I can. Yeah, I'm just getting chopped. Looks like. Yeah, I'm just gonna keep getting chopped. It's very tall. I don't want to wiggle with the graphs right now. So it's very tall, it's around 2. We got a mean theta 2. I think you do it by quantile. I do quantile of theta. Median, and then upper and lower quantiles. Basically, do you agree with this? Well, maybe if I just, let's see first. Let's just set it to the same value and see what's good. So I'm modeling the same number of observations, so it's in theory just doing the same thing. And she wants to know, she saw 24, and she thinks if she had more people to talk to more people, the results would have changed by 1 or 2% at most. So if we look at the mean, post-predictive, right? Mean post-predictive gives us 24. And then say I increase this to 500. And then I take the mean of post-predict. Oh wait, that's not informative, right? Maybe the mean, oh. 300. This is probably not doing what I think it is. So the success count went up. So that's true. Yeah. The average post-predictive increases as you increase the amount of people you saw. Even we base our posterior distribution on what we observed in the data, and she claims that if I see more people, then I would predict that I would get more successes. All right. I think also just looking at the prior or posterior distribution mean. I think I have some code. I just don't remember off the top of my head, which is fine always. But I have some code that will give me I really just want an example of the quantiles broken down. I know there's a way to do it, I just don't remember. Let me see if I can go over here and find the code, because I think it's informative to just look at that. Or at least, I want to look at that, so. This is the stand code. So I like looking at the stand code a lot. I'll probably do more of doing the stand code. It takes a little longer to run sometimes. But as we got more complex problems, I think that becomes less of a problem. Isn't it supposed to just give me a summary? But maybe if I say print. If I print. Oh, it does. That's nice. So print samples will give me that. This is what I was looking at before too. So we have theta success rate here. We can look at the standard deviation success rate, and she said that it would change by like a couple percent, right? At most 1 or 2%. I don't know about that. Yeah. Interesting how the variability changes. Just some things I'm noticing. Yeah, I'm curious too to see if I can find solutions, just so I can check my intuition here. Because for this problem, this is one of the first use case problems where I think there's a clear point I might be missing, or I have to get at in order to make sure I get. Well, I've got a lot from the problem, but yeah, some draft answers, sweet. Interesting. So looking at the credible interval is supposed to give us some insight here. So successes range from 14 to 38. So 13 so that's interesting. So the way it outlines it over here, I'll pull it up. You can look at the 95% credible interval, and you can see this in the graph too, where we're getting likelihoods of the counts here, the probabilities of each of these counts, so how many successes I would have got. And we have a 10% proportion, so out of 121 samples, 10 to 31, so that's a pretty widespread. Or as they say, this is about a 20% spread, considerably more than what they estimated. Right? They said no more than 1 to 2% in the question. So there are at least two sources of uncertainty. First, there's uncertainty about the true rate of bullying. Right, so just because we observed 24 out of 121, this doesn't give us the exact theta. But even in the case where the second source comes into it, namely sampling variability. So you need to take into account your lack of knowledge about the true rate of bullying and the uncertainty related to sampling variability by simulating sampling processes based on posteriors. There are much more sources, and we have to ignore some when we're doing analysis. But here's the point, takeaway. So the moral of the story is that that our moral of this story is that often more sources are there. There are often more sources of uncertainty than you'd expect. And you have to take into account these. So we have sampling variability here, acting. We have uncertainty about the true value of successes. But we know that it's somewhere around there. But like the example demonstrates, there's a big possible amount of proportion. So we can predict this, 121, right? So 11, or 38. So, in this graph over here, 38. And then if we look at this minus this, 20% range. And in the problem, she stated, oh, it's about like 1 or 2%. So there's a lot more variability than we expected. And maybe if we had more data, if we had observed more samples, like say this was like 200 and this was 1,000, right? Ridiculous like that. Yeah. Extra tight. So I wonder if this changes anything. Much less. Much less. Before, we had almost 20% of variability. So now we have 6%. So increasing the sample size really increased our confidence in our observation of the true theta parameter. So we're reducing uncertainty here in the sense that we're reducing sampling variability because we can rely more on the sample we observed to give us a strong, as this distribution shows, a strong or confidence in our estimation of theta. Yeah. Cool. It's a good example. All right, let's keep moving. One important use of the posterior predictive distribution is to examine the descriptive adequacy of the model. So, oh, no. What if I can do highlights here? I really should switch over my PDF. I've heard good things about highlight. It's another way of doing Adobe stuff. It gives me a lot more flexibility and access to stuff. Or at least that's what I've seen in some YouTube videos. Or just switching over and doing these edits in LaTeX. I'm not really big yet, or in Zotero, but I'm not really big on electronic note-taking just yet. In fact, I'm really like, obviously, and love paper copies. That's why I have the book copy. But all right, so it can be viewed as a set of predictions about what data the model expects to see based on the posterior distribution over the parameters. So it's essentially saying it's a great way to check. All right, so we updated our priors. We have this posterior. Let's put it on some data. Are we doing all right? Is this an adequate, or is this a good enough representation so that we can make inference about whatever the parameters mean in that case? So let's do some model adequacy checking here, and we're just going to look at the common rate problem again. So we have a success rate, we have two data sets, and they have this underlying latent success rate that we didn't observe, but we observed success counts for the two. So you can imagine this being two populations of people, maybe, or two people. It could just be two people, and they're flipping coins, and we have success rates for the coins, and we want to know, if they're using fair coins. We have two populations to observe that. But since they're the common rate, you could probably just cube this. I think there's an example of cubing it up here. Or here. So this is also common rate, right? Since they're the same, you can represent it with that. And then use subscripts. Why we don't do so down here, I think because, I don't know. All right, so let me open the code 5. Oh wow, I'm all in the wrong place. Gotta go back. Nice thing about having all these resources is, well, having the resources, but putting them in the right folders and stuff. I really just got to keep up on that, and that can get challenging over time. See, I don't even know where I am. Where am I? Here. No, see, I want books. There. Primary message. Binary. Let's get jag5, and we need the text file too. Cool. All right. Seems to load okay. The plots, once again, looks like they're as good as they're gonna get. Yeah, that's fine. Look at the code. 2 amounts of success, 1 common rate, 2 plus this predictive posteriors. So 2 different data sets that we're going to predict. And we should be predicting them about the same because they have the same rate, right? So even with sampling variability. But in this case, they're the same rate. Even with variability in the sampling rate, or the number of samples, they have the same rate, so we should see similar patterns. Here, where this is just the plot we saw before, but now with the largest squares representing counts for probability, yeah, like discrete counts. And then the x, I don't know what the x is. Let's take a look at the code. It represents 10 successes. I think. 10 successes? Not likely. Five successes? Likely. This makes sense-ish. I mean, we're pushed in the middle where our first data set saw all successes, our second one saw none, right? So we're pretty in the middle here. So what does it want us to do? Why is the posterior distribution in the left inherently one-dimensional, but the posterior predictive distribution on the right is two-dimensional? Because we have a common rate for one, so there aren't two data parameters. There's only one. And when we're doing prediction, we're using two data sets. We're using the two data sets that we observed, which we used in order to update our priors. Right, so we used all the information from both data sets to update the priors. But you can imagine, because it's the same rate, they didn't have to be two data sets. We could have just combined it all into one, and then it would have been this. Unless there was information about that we thought that was unique about the two data sets. But then we would define two different rates. If they come from the same underlying rate, I would think that you just want to combine them. Maybe that's why we do that other graphical representation where we put the big rectangle around it before. I don't know. What do you conclude about the Oh, before I move on, the right panel is inherently two-dimensional because of these two distributions, right? We have two distributions, and we're doing predictive checks on both distributions. And you can imagine that the predictive check for one group, which had a high amount of successes, right? So group two had all success. But when we take it to the predictive model, we're seeing that we would predict differently, where we would predict values up here. 6 and 7s are most likely to occur. Or we see more 6 and 7s, right? 6 or 7 successes rather than 10. And part of that is because the success rate for the first data set is 0. What do you conclude about the descriptive adequacy of the model based? I say it's pretty poor. I was really successful in one, but I really wasn't successful in another. Why is this different? It's kind of just meeting me in the middle. It's a 50-50 sort of thing. It's like chance. That's what I would conclude. Oh, so now that we looked at just predictive checks across multiple data sets, let's look at let's look at distributions of posterior distributions jointly. So rather than just looking at one density, we're looking at multiple together, I think. Yeah. So we're going to be looking at the posterior distribution, but for two. Well, let's read on. Today's posterior is tomorrow prior. This graph is just showing, so we can start with some uniform prior. We can do some prediction. We have this predictive data. We can use this predictive data. We can make we can update our priors again from what we observed. And that's using our new prior, right? So this data has priors. So this data gives us these sort of priors. And we can use these priors to do prediction again, and et cetera, et cetera, et cetera. So we can keep doing this. So it's good we can constantly be updating our beliefs. What is the example? There are always more than one more variables of interest that interact. So this time, we don't know how many total samples we have. We just have information about the number of successes. Suppose there are 5 helpers distributing a bundle of surveys to a house. Let's go ahead and open our surveys. So the JAG survey, text, I'll move the text over. Let's clear it up. I think this, we're just going to do these joint distribution problems and then we're done today. Alright, so each bundle contains the same number of surveys, but we don't know how many surveys that is. We only know that we have a threshold of 500, so no helper had more than 500 surveys, so the survey count has to be between 1 and 500. But we also don't know the success rate. So we don't know how many surveys someone actually delivered, and we don't know how many surveys they had. We really were struggling. So what's the rate of return for the surveys? Given that we have information about how many surveys an individual reported successfully distributing, not how many surveys they had or the underlying rate. So M5 for each helper, and we have this. So this is a little more complex than what we've seen before. So now the observed returns, it's nested. So we have for I in 1 through M, so for each of the surveyors, we're going to ki, so for the success rate for a given surveyor is a binomial distribution for this, and n with success rate and amounts of surveys. And we don't, so this is interesting because we don't have any information about, we don't know the rate and we don't know n, but we're going to estimate those for each of the subjects. So our priors then, we're going to use an uninformative prior, and now we have n, which is distributed as a categorical, and an empty list here looks like p. And now we're going to use a for loop to fill p. So p is going to be I to, it looks like p is the total number of surveys, what we're using. Is it the probability of total number of surveys, or is it just the number of surveys? Predicted number of surveys. And it can range from 1, so they definitely had to have 1 or else they wouldn't have been a survey helper, or 500, which they said. But we're not putting that restriction here, which is weird. Oh, well, we specify the prediction somewhere else. So here we go. Excuse me. So now we observed k at these 5 values. So let's move over to the code now. So we specify n max here, and we observed. If the max is 500, we have some lazy survey folk, I will say. And then we need the length. Why did we need the length? We need the length of how many helpers. So this is the number of helpers. In this case. Oh, it takes a little bit this time. Oh, but the graph looks great. Oh. It gives me this ugly graph to heat up. We're just gonna I just wanted to give me the list for now, because these are pretty. Even there, you saw it changed a little bit. Wow. Oh. Let's see. A little sampling variability go a long way. So we have return rate. This is theta. Is it theta in this case? Yeah, theta. And then we have number of surveys, maximum 500, minimum 1. We have observations. And this x and this green point are representing. The circle shows the mode, so it's the maximum likelihood. It's what the frequentist estimation strategy would give us, right? Both estimated from both samples. The cross shows the expected value of the joint posterior. Oh, so this is the maximum likelihood. And this is the expected value of the joint posterior. So the joint posterior gives us a different average than does the maximum likelihood estimation for both of them. So we're getting conflicting evidence, and we can only see this by modeling the joint posterior. I think that's the point they're trying to make. It is clear that the joint posterior carries more information than the marginal posterior distributions. Quote, very important. This means that just looking at the marginal distribution doesn't give us a complete account of inference, so it might be misleading. The basic moral of this example is that it is often worth thinking about joint posterior distributions over just the model parameters. Looking at both. In this case, the marginals were probably misleading, potentially even more misleading are common point estimates, so not looking at distributions whatsoever. Notice that it does not lie in the parameter space. right? So it's just referring to looking at this expectation here. I see. And look how uninformative it is. It's somehow missing some piece of information that the joint distribution is accounting for. Does it make sense? The posterior mass is represented expected value of the general posterior estimated from the samples. So just looking at a sample, we're not getting an expectation that corresponds with that. I don't know. It seems unhelpful to have a point summary that is not plausible estimate of the true underlying value. One way to think about this result is in terms of the goal of the point estimate. The mean in this example is trying to minimize the squared loss of the true value, and the possible value follows a curved surface. So while the curve, okay, so expectation-wise, it's not representative. I mean, I get that the mean can be represented, so this is the mode, this is the mean, and they're different in that they have the same underlying rate of return, but the number of samples is different. Number of samples that it would predict is higher for the mean, but it's not the most. Yeah, that kind of makes sense. All right. The circle shows an approximation to the mode. So where do we see most of the density? Most of the density lies for samples that are here and samples. So of the combination of these two parameters, where is the highest probability, right? Let's see. Falls in value is the highest density in the estimated posterior. Think of sitting at the top of a hill surface traced out by the scatter plot. Nonetheless, it seems unwise to try to summarize the complicated and informative curved pattern by a single set of values. Yeah, so why both these instances are point estimates, so not that good. It's just to demonstrate. Traversing this, it's the point at the tippy top of the or the model's landscape of the parameter space landscape. It's like at the tippy top of both of these. It's a good workout. Two more questions. Good. All right. Try to slightly change these values. How does this change the joint posterior? $16, $18, $22. I'm going to put it over here, and I'm just going to change the values in real time. So instead of these, it wants me to change 18, 22, 25. So I'm literally one value. Wow. Well, the mode moves. So the mode becomes higher. The rate of success becomes lower. So I've increased my number of total observations. And now it's telling me we have a lower probability of the success rate is lower based on what I saw with more data. And the expectation and the mode are closer to one another. So a big shift to probably 200 now rather than 100, just from moving one sample. I think I'm less comfortable with the mode now. It seems very variable and not reliable. Right? I just shifted so much from one change. What if I do this? Oh, goodness. Very sensitive to these 5 success rates. A success rate of 29 out of 500 really puts a lot more predicted number of surveys. Shoots up. Right, because you see it keeps increasing, so it keeps evening out the possible. 500 becomes a maximum of 500 becomes more possible and more probable as we increase the number of successes. It tells me, oh, there were probably a lot more surveys because I think the success rate is so low. So I need to have a lot of surveys then. Interesting. What did the book have to say about that? Minor change to the data hardly affects the mean, but greatly shifts the mode, right? So mode's very sensitive to the exact information. Altering it slightly really moves everything. Alright, so if you look at the sequence of samples in a trace plot, some autocorrelation is evident. The samples sweep through high and low values in a systematic way, showing dependency of a sample on those immediately preceding. This is a deviation from the ideal situation in which posterior samples are independent draws from a joint distribution. Try thinning the sampling, taking values at 100th, reduce the number of samples to 500. Alright, so we're just going to change some of the parameters in the sampling strategy. So here, instead, we're going to taste thin to sample every 100th, and then to make computational time reasonable, reduce the number of samples collected after thinning to 500. Run 50,000 total samples. So because we're doing 100, we're grabbing a sample after every 100, right? So that makes sense. So oh boy, this might take a while. You know, and maybe I can find some code to show me the trace plot. I don't know if I would do that. But yes, it looks like I can just call trace plot. Of the samples. I mean, I'm only doing one chain. We can see how it's I see, so let me change that, save that. Let me get the trace plot here. So, a lot more spaces. I mean, we're sampling from each of the, so this time, do 100, like it said, and then 50,000. This should take a second, and then we do the trace plot again. And it will let us to identify these thinning differences. Oh wow, so I should change the chains too. So let me also, I'm just reading one of these notes. It said I should pick up the chains so I can see some of the mixing too. I'll do that. you can already see less holes, more stochastic, less dependent on one another, maybe is the way to say that. See how values tend to follow this really closely to one another, right? But here, the last value, it could be up here, it could be down here. It's far more stochastic. That looks good. Two chains. Number of initialized chains is not equal to n number of chains. Now we got the chains. Two chains. I don't know what mixing is, but maybe this is it. You can see the chains are sort of giving us different values. It's the last one. This will probably take a sec too, so I'm just changing the thinning on both the chains so I can try to capture this effect that one's going to see. So I'm getting 500 samples are retained here. And I want to look at how visually this varies when I change the sampling strategy, or when I thin how I sample from the Markov chains. I don't know what to call it yet. Or just a random sample from the prior distribution, or a random sample of it's a random sample of the marginal likelihood, right? I think. Let's take a look at the trace plots. That looks mixed, but also look how much more, I mean, human eye, right? Much more stochastic, but just much more stochastic. This to me looks like it might be following some sort of trend as it moves. I mean, this doesn't, but interesting. Well, today went a lot better than yesterday. I think I'm going to stop there, so next time we'll cover some more. Let's take a look here. Yeah, so next time we're going to start with inferences from Gaussian distribution. So we're going to start doing models like this where we're going to have total data we observe, and we want to try to get at the parameters of interest. So the first two moments for a Gaussian distribution, and we'll learn how to specify that. Cool. Interesting. Yeah, this has been going well. So thanks for hanging out if you were here, or thanks for stopping in. And I look forward to continue doing these examples, and I'm keep working through some of the logistical issues, but this is good. All right. Catch you next time.